For those of you that don't know me, I'm Robert Goodrich. I'm president of the IEEE branch on campus this year. I want to talk a little bit about grad school. Something that's very important as engineers and something that's sort of expected of us is that we go to grad school whether we want to or not. Something that kind of is a struggle for us, though, is that we don't always get a lot of information about grad school. We don't know what to expect. We don't know why we should go. We don't know the types of things we're going to be doing. Our professors, though, can give us that insight, and in line with that, I want to thank Dr. Rumbaugh of the Electrical Engineering Department, Dr. Brooks of the Electrical Engineering Department, and Dr. Richards of the Mechanical Engineering Department for offering their time here today. They can each offer a unique and different perspective into how graduate school works. And I would really encourage each and every one of you to do your best to take the most out of the room today, do your best to learn, because this information could literally affect your decision of whether you're going to grad school one day. So without further interruption, I want to just welcome Dr. Brooks.
So thanks for the invitation to come share a little bit about my experience with you. As you guys know, I'm new faculty here this semester. So I've been out of grad school for a number of years, but I can at least relate to you kind of my experience. I had a bit of a hybrid experience where I worked before going to grad school, during grad school, after grad school, and so it's I don't know how typical it is, but I can share with you my experience and give you a chance to ask questions about that. So the first thing, I'll just describe a little bit about kind of how my career launched. So I graduated from here, in electrical engineering department, and took a first job at GE Transportation up in Erie. It's now part of Wabtec Corporation. I was on their technical leadership development training program. It's one of these 2-year programs that you rotate every 6 months. So I did jobs in microelectronics, laying out PCBs and qualifying vendors and all that kind of thing. I did power electronics, 1,000 horsepower inverter design, these kinds of things, and then settled into control systems design. And during that, I did a bunch of coursework. We did technical work. We did what's often called the GE MBA. GE has a kind of a corporate university in Crotonville where we teach leadership and finance and marketing, all this stuff. So it's a great way to kind of get started. And as part of that, they would allow us to go into a master's program. And so I did a part-time master's online at Georgia Tech. So I did that in electrical engineering, focused primarily on communication systems design, something I've always been interested in. And so the interesting thing about the Georgia Tech experience is that I never stepped foot on campus. And as of today, I've still never been on the campus of Georgia Tech. I've been by it for a bunch of meetings, but so anyway, it's a very interesting kind of experience, and I think that's becoming more and more common. So let me just make a couple of observations about the master's experience by itself. The first thing I think that really hit me getting a master's degree is that the realization that engineering is really broad, and I mean really broad, right? I mean there are topics upon topics in which you could study and take courses in that you may not have even known existed. And for me in particular, there was an entire discipline that I was unaware of as an undergraduate student. And that's kind of the broad discipline of systems engineering, operations research, human factors engineering, all three of these things I was not aware of, right? So the grad school experience exposed me to those new areas and ended up doing my PhD in that area. So really, the other main differences I want to just talk a little bit about is, courses in grad school are different. In two ways from my perspective, and I'm sure that these guys will give you their perspective as well. The first is just the pace, right? Coursework goes a lot faster in terms of the material that you cover, and often not everything is covered in class. And so you end up learning on your own, and so that's a skill I would really encourage you to press into now as an undergraduate student. Become comfortable teaching yourself, because if you go to grad school, that is what you'll be doing an increasing proportion of the time. And then the other thing is depth. So I mentioned there are whole courses, right, and topic areas that you don't have at the undergraduate level. And that's just because it's so broad, right? There's so many things to do. And so you'll have courses that are very specialized. It goes very deep in comparison to the courses you take as an undergraduate. So those are kind of my main observations there. The other thing I wanted to talk a little bit about, there are a couple of different ways you can get master's degrees, right? There's a Master of Science, which is kind of a traditional research-oriented degree, which can either be a terminal degree, meaning the last one that you get, or on your way to a PhD. And then there's a Master's of Engineering, which is typically a terminal degree. And a Master's of Engineering would typically be more of a practice-oriented graduate program, where you would focus more on coursework than thesis, right, or doing any kind of research. And of course, this is not a hard and fast rule for me. My degree is a Master of Science, but I did not do a thesis. I did only coursework. And so there's a lot of variation there. So it's just, think about what kind of experience would fit your intended career path, right? What kind of education that you would like. So I just wanted to talk a little bit about the work that I did in the interim. So I mentioned I was working with GE Transportation, and they build locomotives, which most people think of railroads as being old technology. Of course, the Continental Railroad has been out there for 200 years, whatever. But really, there's a dramatic revolution happening in technology for these vehicles, and I've been able to, fortunate enough to be in the middle of much of that. These are a little hard for you guys to read, but essentially what we've been doing is looking at ways to make the asset smarter through automation and through communication technology, with machine learning, all kinds of things to predict failures and operate more effectively. And so I wanted to talk to you about is the one that I spent a lot of time working on, which is the automation system. So we call it a trip optimizer. This is the interior of a locomotive cab, and you have the engineer is sitting in the seat on the right. They're not an engineer in the sense that you guys are trained to be engineers. They're locomotive engineers, but same title. And so they're surrounded by dials and gauges and things. And we built this system, and this is what it looks like on the screen, to show them how you should drive a train to maximize fuel efficiency. So there's this big optimization problem, and then a control system that drives the train to meet the optimum speed. And so the reason I bring this up to you is to say that in the process of working on this project, we went from a team of 5 to now there's about a team of maybe 200 people that today are working on this product. It's now deployed around the world, right? We went from research phase to initial commercialization to now where this software, so I was the lead control systems engineer for this product, and right now it's running maybe 2 to 3 million miles per week in automatic control in trains all around the world. And what I experienced doing this, though, was realizing that there was so much we didn't know about how to design this. And in particular, we've got a human operator that's sitting in front of the screen, interacting with this control system, and we, for all intents and purposes, ignored that person, right? Even though they were the expert and they were the ones that determined our success or failure as a product. And so I started to think a little bit about how do we quantitatively account for humans in our design, and that's really what led me to go do my PhD. Is that I had this kind of burning desire to understand socio-technical systems, right? So systems that have technical components like control systems and people, and how do you think about this interaction? And so that drove me to do the PhD, which I did at Rensselaer in Troy, New York, which is adjacent to GE's research center. And so I transferred from GE Transportation to GE Research, and I continued my career with them and took a leave of absences to go to classes and do research during the semesters. And so then I would come back every summer and then go back to the university. So I was going back and forth for the 4 years that I was doing my PhD. The topic I had there was looking at disaster recovery. So in particular, we were working with the Army Corps of Engineers to improve the process of cleaning up debris after a tornado or a hurricane, right? Any kind of debris-inducing event. And the interesting thing about these problems is you can model them mathematically, but there's a lot of people involved making decisions that you don't have any control over. And so the question is, can you model that? And if so, can you influence them to make better decisions in a way that is distributed and doesn't require any kind of strong arming? And so that's really the focus of the research that I did as a PhD student. So just give you a sense of what that looks like. And again, the intent here is just to show you some of these subtopics, that you can spend years and years of your life making progress in the state of knowledge in a really small subtopic. And that's really what a PhD is. And by the time you finish a PhD, what you realize is you know a lot about a little thing, and you realize you really don't know anything because there's a lot of little things to go study. So it's a very humbling experience. But here's what the crews that clean up debris, what their work looks like. At the top you see a small team of people with like a bobcat and a truck or a trailer, and they're loading stuff up. and then they're going to drive it off to a site, which is at the bottom, in which case the debris is unloaded and it gets reduced, right, through chipping and shredding, and then it gets hauled away to other locations. And so this kind of a system we were able to model as a queuing network, a network of queues. So a queue is where you have machines providing service, and then in this case trucks waiting to either load or unload. And so this kind of queuing dynamics is well studied in stochastic systems for things like computer networks, many kinds of transportation service systems, call centers. It's a very broad and nice, I think, mathematical theory of systems, dynamic system behavior. So we built a model of this. We had a bunch of data from a big event in Alabama that the Army Corps helped us to get. And of course, this is a network, so I'm showing you one loop. There are many of these loops, right? Hundreds of teams working in a very large geographic area. Like in my case, it was the northern half of the state of Alabama, over a 40-day period while they cleaned up this mess. And so the engineer in us would say, okay, I have the model. I want to optimize the performance, right? So if I could control every single truck, I would tell them exactly what to do, and everything would be done quickly, which is true, right? So we solved it in a traditional operations research way, formulated a big nonlinear optimization problem, and solved for the best possible solution. But of course, I have multiple organizations making all these decisions, and they're all getting paid, right? There's some policy set by the Army Corps about how they get paid. And to my knowledge, that policy was set arbitrarily. Like, how do you think they should be paid? I don't know. How do you think, right? And they just pick something. And so what I was able to show is that actually using these mathematical models, there's an optimal way to pay folks so that they get paid more and do less. I mean, everything happens in a shorter period of time, right? So you get paid more per hour. The total cost is less, but the time is shorter. And so really everyone benefits, right? The communities benefit, the government benefits by paying less, the contractors benefit by making more per day, and everybody wins, right, with a little bit of science and math and engineering. So so we did that, but then we had to understand, well, people make decisions for lots of reasons. So we studied that, built a model of human decision making, and then tested the whole thing out in simulation, right? So it's a very, very kind of broad intermixing of disciplines. So that was my experience at PhD. So just let me make some observations, and then I'll let these guys talk. You're just, again, comparing and contrasting, right? So I said before, the master's made me realize engineering is broad. You get to the PhD and you realize, no, it's really, really, really broad, right? And so I narrowed in on 2 or 3 subtopics of two or three different fields, actually. And you spend all of your time there, and you make a little bit of a dent in the knowledge of the world. But there's a lot of things to learn. So just the differences with the master's. As a PhD student, you are required to take courses. Grades don't matter. Your research matters. And so typically you would focus on your research rather than on your coursework as a PhD student. And grading is very different. No one gets a C. It's an A or a B for whether you were there and breathing or they're not there and not breathing, right? Those are the 2 options, basically. And the reason is that everyone is working hard, right? Everyone's there to learn, and everyone's doing their best, but they're focused on their research. So PhD is, at least for me, was a very different experience than as an undergrad, because your focus is different, right? Your focus is on engaging the international research community, making advancements in the state of knowledge, and sharing that and getting that validated with experts in your field, right? So it's just a different focus. And the other thing I would just encourage, that I think cross-disciplinary work is very fun, right? And I think that's the world that we're in now, is that a lot of opportunities exist between disciplines. And it's hard to do work in that area, but it's incredibly rewarding and a very rich place to explore. So that's all I have to share, so we'll pass it on.
So as I mentioned, I'm Geo Richards. I'm also a new faculty here, but I had a whole career before this one, so I thought I'd give you a little bit of background on that, maybe what brought me here. I graduated in 1987 with my PhD from Purdue University. Boy, that sounds like a long time ago, and I won't go into all the details. I was on a path to go teach in an academic environment and had 5 different jobs offered to me, and God told me clearly to turn them all down, which was very discouraging for me because I thought that's why I was training. But he opened up something so more wonderful, and that I did the next 30 years. I started as a researcher for a laboratory in Morgantown, West Virginia. At that time, it was a federal lab facility, eventually became a national lab, and did energy research over that whole time. And I will tell you, I had a lot of fun over all those years, including my graduate school days. I really enjoyed it. I often told people my big mistake was graduating, but you know, I had to eventually leave the place. I had so much fun. But let me tell you about some of the things I did along those 30-some years because I had that background in training. The comments about interdisciplinary that Dr. Brooks just mentioned, that was just a great privilege to work with so many people across different fields. I tried to make a list here of some of the more interesting things that went on over those years. I was able to do work in acoustics and thermoacoustics. When I started my career, there was a crisis going on around the country. There were power generating turbines just shaken apart because the combustion was not stable with new emissions. We actually solved that as a lab. It was a very exciting time. We implemented something called active combustion control. It takes dynamic control systems and sticks them inside of this fluid mechanical system. We actually were one of the first places to develop something innovative technology that's used to eliminate CO2 emissions. But the technology we developed required us testing this oxy-fuel combustor in a hypersonic wind tunnel at NASA. And I'll never forget that experience because we're sitting in control room. It was the one there you're normally running a high-speed engine in, and we're sitting there with all these folks, the headphones on, the gears, doing the countdown, running this thing that we had the privilege of building. Look, I could go on and on here. I mean, I was able to do all these different things. I think the most recent interesting one was I was doing geothermal energy in the eastern U.S., believe it or not. There's a shot at it here in the eastern U.S. But the only reason I could do all those interesting problems, start to address them, is I spent that couple of extra years maybe with the discipline it took to get through graduate school, and I just say that was a tremendous blessing. I hope I was able to contribute in all those different projects I was involved in. I ended up leading a lot of that, and finally finished my career. I was leading all the energy conversion work at our lab. So it was a great experience because of that training that I took. Now, I'll also say the other piece of this, there was a great opportunity to network with real innovators in my career and then also in graduate school itself. So before I get into graduate school, I just thought that first bullet there, interesting problems to solve. I wanted to show you one we were working on right when we finished. Right when I finished, my lab's still working on it, but it cuts across so many areas, and it's to underscore this point of cross-disciplinary work. So how do I turn this? Is it up here? Right here? We started working on this technology called magnetohydrodynamics. The physics majors might recognize that phrase. It's the process by which solar coronas are controlled and they form that big arc. There's a magnetohydro, meaning fluid dynamic motion, those interaction of those two things. There is a possibility to create extremely high efficiency power generation with this technology because unlike the things we build to make power today, those are all limited in terms of the top temperature that you can operate because you have to contain that high temperature fluid and do something like expand it against a piston or flow it through a turbine. But there's another way to pull power out of it directly, and it's shown on this slide. The label A up there, this turbo generator, you can see that magnet with a conductor in it, conventional generator. The way that generates electric power, that wire moves and cuts through that magnetic field. It creates a voltage running across that wire, and you generate power. That's how we generate power today in almost every application. The key is that you've got this conductor moving through this magnetic field. Well, you could also have, instead of a wire, you could have a gas moving through a magnetic field. And if that gas was conductive, and you put two electrodes on either side, you can actually extract power just directly out of that flowing gas. And this idea is not new. It had been tried a couple of different times, but we realized there were so many advances going on in magnet technology, materials, and we had some other tricks that we knew we could try to incorporate. We said, let's take a look at whether we can actually make this into a viable power system with efficiencies that are just unbelievable. So for people who are worried about CO2 emissions, it's a way to make power from hydrogen-oxygen combustion, for example. No CO2 whatsoever, right? Problem is, no one knew how to build this. So we started a project to actually understand whether we could build such a device. And I just put some of the interesting images up here from work that was going on. We started in a little laboratory burner that's about a 1-inch square burner that we're flowing that hot gas out, and you can barely see the image. This was so bright, it's about 5,000 Fahrenheit. You can see that probe, and we would just go in to measure the conductivity and pull it back out. We were starting to work on a microwave technique to actually measure the conductivity of the fluid, because we need to know how conductive it is so we can find out how much power can I pull out of that flowing fluid. We started there, and then we moved that on from just a laboratory to actually, this is the small nozzle, and I think you can see here these diamonds. Those are the so-called shock diamonds. If you've ever seen a fighter jet on takeoff, full afterburner, there's all those diamonds coming out of the back, or a rocket engine, because it's going above supersonic speed, and you're actually collapsing the flow. So that's what that nozzle is doing. We're trying to get this high-speed flow, high-temperature flow to come out of here. And then up on the top, you can see one of our first tests of the side electrode coming in to actually start to try to pull power out of that particular flow. So to make this work, all right, imagine trying to get that electrode to survive at those temperatures, those flow rates. We're actually making pretty good progress. That one that you see there actually survived fairly well. But I had to collaborate with people who are material scientists. An area I don't have great expertise, but boy, I started learning it, all along the way. Reacting flow, that's an area I do know a little bit about, so I was able to contribute there. The electromagnetics, I got so interested in that, I just started to teach myself. The comment Professor Brooks made, it's a key part. If you think you're going to go to graduate school, maybe go into a research career, better start to teach yourself, because you'll just keep encountering new problems all along the way. I became very interested in plasma behavior. I'd had some background in chemical lasers, so that was not totally new to me, but I had to start collaborating with people who were really experts in plasma technology. The diagnostics, so we could see the chemistry of what's going on in there. We developed the whole activity there as well. And last but not least, Professor Brooks mentioned system engineering. This is all fun technology, but the other piece of my job, and probably the bigger piece, was to sell it. To convince people as a system it could work and it was worth spending the money on the research. So that's a big piece of what you'll do in your career, probably if you're in industry or if you're in academia or in a research lab like I was. You have to convince people it really makes sense to pursue this technology because you're going to invest so much in developing the technology. Well, let's get on to a couple more personal things here. The other thing about going to graduate school, it is just a great opportunity to network with the innovators, the leaders in the areas where you're working. I remember so clearly, I had a very well-known professor in graduate school. I'd go to a meeting to give a paper, like, these young people are there maybe presenting their own research, and people would say, well, where are you from? And I'd tell them I was working with my professor, Arthur Lefevre. And it was just fun because you'd get this immediate reaction, oh, you poor guy, because he was that kind of a guy, right? He was a wonderful person to work for. But you will network with people and learn from them in ways that's just amazing. I was at a meeting just about a year ago, walked into a room. It was a very selective meeting, all invites of researchers from around the country. Walked in and met a guy I had been in graduate school with, hadn't seen him in 30 years. He'd risen to the top of his corporation, and there we were again kind of talking about all the things we'd learned over the years. So it's a great opportunity to network with the people who are leading your area. I couldn't resist finishing off with a couple of more personal comments, because this is what you're probably thinking about. Graduate school, was it difficult? Could I succeed? I'm just going to say, pray and ask the Lord, is this for me? Is this what you would have me do? And don't worry about it after that point. He'll help you with the rest, right? It may be challenging, but I had a blast in graduate school. I did. I enjoyed it very much. I walked in with a lot of trepidation could I really do this? But I found out it was actually a lot of fun and enjoyed it all along. How do you know if it's right for you? One last just sort of personal story here. And I would ask you not to spread this story too far, because it's very personal, all right? I have a son, a mechanical engineering graduate, and he was getting close to completing his bachelor's degree in mechanical engineering, and I had watched him go through school, all right? And I kept thinking to myself, this guy is material for graduate school. And he kept thinking, I don't want to go to graduate school. I just don't want to go. I'm tired. I don't want to do this stuff anymore. I just want to get a job, right? And then he started getting close to the end, and he was busy, and he was a good student, right? He started looking at jobs, and he realized none of those just like excited him. Just wasn't all that really exciting. He was thinking about it, and luckily he delayed long enough. He procrastinated long enough. It was like, well, I'll just start looking after I graduate. And right in the midst of that, an opportunity opened up in a lab that he is now working in as a graduate student and loving. He just didn't know. And, you know, Dad can't say much, right? And you can't, right? I mean, it's got to be his call. It's got to be your call, right? It's got to be something you and God speak about. But he's loving it. He just didn't know that about himself. So is it right for you? Pray about it. Think about it. Maybe talk to some people who are graduate students today. If you need help finding them, I'm sure we can get you connected to different graduate students in all kinds of schools and topical areas. I've taken way too much time here. Next. So, thanks.
Hi, everybody. I'm Luke Rumbaugh. I just joined the electrical engineering department this summer, electrical and computer engineering department this summer, and I'm happy to be here. And I wonder, you guys are here for several different reasons. We understand. How many of you guys are actually considering or have considered the idea of going to graduate school, though? Okay, good. All right. So there's some active interest. So I don't think when I left college that I thought I would be, going to graduate school. And I followed a little bit of a weaving path, I guess, to get there. I don't know if I'd recommend my path, but I'll tell you what it was. And I'll tell you that I'm glad I went. But I think I would have been happy not going as well. So I'll tell you more about what I did. So I graduated from Grove City from here in '07, and in electrical engineering, and I'd say without a particular focus. Like I'd worked on a little bit of robotics, I'd worked on a little bit of maybe communications a little bit, but without a particular passion for, oh, this is a particular technology that I'm really excited about. But as we know, our mechanical and engineering degrees are quite broad, right? The idea is to prepare you for umpteen million different jobs or things you might be interested in. You could go all the way from aerospace to chemistry if you wanted to. So I ended up landing with Johns Hopkins APL, which is down in the DC area, and I was doing work for the Navy on ballistic missile defense. So got my little cartoon there is we were the Navy and the Army had we were the Navy and we had ships with radars. The Army had ships with radars. And so my main job was in analyzing the data from our test flights and trying to decide how well we were coordinating with our Army tracking and whether we could do better and how we could change the algorithms that way. And to tell you the truth, I was pretty ignorant about how things worked. And so I got bored after a year and a half because I just didn't ask the right questions and didn't understand what the place was. It was a place of 4,000 engineers. About 60% of them have PhDs. There was tons of stuff going on. But I was like, I don't really like the MATLAB code that I'm writing right now, so I guess this place is boring. My mistake. Anyway, what it really was that I was on a group that was doing 20-year out kind of work. And so there was nothing hardware about it. There was nothing practical about it. That's not quite true, but there was nothing in the moment about it, right? It was all big, long-term forecast stuff. And that didn't suit me as well as I thought maybe it should. And so when the opportunity came up to go to Dubai with Bert Hill, now Stantec, I took it, and that was a really interesting experience because that was for 2.5 years of working on the technology side, but in a fairly modern city, really. But of course, you're surrounded by this old tradition, right? And you've got collisions of people from all over the world. Dubai is about 80% expatriate, so it gives you an idea of the variety of people. You could be sitting at a table with 20 people, and there'd be 18 countries represented, and 4 continents probably. So So that was really interesting. The work that we did was basically to do power layout and backup generator systems, lighting, stuff like that, building control systems, HVAC control systems for hospitals. It was fine. Technically, it was fine. It was not challenging at all from a technical point of view. So it was like Ohm's law and how many times can you apply it. So it really wasn't technically deep at all. But it was, every job has its challenges. So it was programmatically challenging. There were hard deadlines and there was big coordination schemes and you met with all these subcontractors and whatever. So, but again, I was kind of primed that when we started having kids, and started thinking about coming home, then the opportunity came up to go to grad school up at Clarkson University, which is in New York State. Hang on. Oh, I guess really I was primed even while I was there, I started doing night classes. RIT had a branch campus there, and so I started taking master's courses there, just kind of dabbling with the idea of at least getting a master's, maybe going back to school. And I did find that kind of invigorating, I guess I'd say, from a technical point of view. After dealing with Ohm's law and spreadsheets all day, I was like, oh, some real challenge, I guess. So I was pretty primed. When family reasons brought us back stateside, then I hunted around a little bit and ended up finding a place up at Clarkson University in the northern tier of New York State. And that was great. I really enjoyed it. So I was there for 5 years working on my PhD, and it was in sensor development for the Navy. So the Navy's very interested in finding things underwater. As you can imagine, they're interested in finding things in dirty water often, harbors, coastal environments. And so I worked on some sensor development for them. So on the laser side, like laser development, signal generation, signal processing, a little bit in image processing. It was really fun. And I think that's one thing I would pause here and say was that when I got to grad school, I was like, oh, I liked the technology as an undergraduate. I just didn't have time to enjoy it. I didn't make time to enjoy it, I guess. Undergraduate experience is 5 or 6 courses at a time. You're doing, 16 different things every day. You have about 2 hours for that homework assignment, and that's as much time as you get to think about transmission lines. Next subject. You know what I mean? So grad school was, for me, like a very enjoyable, basically technology bath of saying, okay, well, we have a hard problem. It's going to take really deep understanding of the technology, so we got really deep into it, and we spent, 5 years, so that means we spent hundreds to thousands of hours on that laser and how it worked, on that signal processing system and how it worked. So you can either think that sounds really boring because who wants to think about something for that long, or you can think that sounds like, finally, I have enough time to do something that's interesting enough and complex enough to be satisfying. For me, it was more like the latter. Okay. When I was at Clarkson, I finished my PhD, and then those of you that do a PhD will find out that you have the option to then do a postdoc or go work. For family reasons, again, I chose to stay and do sort of a glorified postdoc where I was doing research. I was still doing research actively, and then I was teaching for the department as well. And so that got me broadened back out, I'd say. James mentioned that things narrow in when you're in your graduate school studies, and you just sort of dig in on one topic for a really long time, right? And so the teaching kind of started to broaden me out, and the experience of being a principal investigator where you're kind of running your own lab, then you start doing multiple projects rather than just being a grad student is spending your own time on one project, all your time on one project. So I did a variety of stuff there, as you can see. This slide is borrowed, as you can tell, but the reason I kept it in here was I wanted to emphasize a couple things about graduate school for those of you considering it. The first and most important is you should not pay for it. If you're an engineer going to graduate school, if a school accepts you and tells you that you can come if you pay, that means they don't accept you. And there's not going to be a lot of room for you there. There's not going to be a lot of opportunity for you there most of the time. Your mileage might vary. But if you get accepted and a school actually wants you, then they're going to offer you an assistantship. So you'll either get brought in as a TA, that means you're going to teach for your tuition, or you're going to come in as an RA, meaning you'll do research for your tuition. In my case, a lot of people start as a TA and get transitioned to an RA. I was lucky enough to start directly as an RA. So the Office of Naval Research and this facility down at Patuxent River, Maryland, basically paid for my PhD all the way through. And that means that I spent most all day, every day, like I was saying, developing those sensors. Yes, going to the classes, but basically while you're in the classes, you're sitting there thinking, how can I apply this to my sensor? You know, that's really, literally what everyone in the class is thinking is, how does this apply to my research? So it's good for us as engineers in that you should get your tuition paid for and a stipend of, call it $25,000 a year or something, supposed to be enough to buy you, enough soup to subsist on. So debt is not a huge factor for grad school, unless you're stupid and you do it while you have a family, in which case, talk to me about that. The other thing I wanted to emphasize here was that graduate school becomes, by its own nature, very collaborative and very self-directive. So this was my boss, my advisor, Dr. Jemison, and he was great. But we were studying really hard things, and like he didn't know, right? He didn't have the answer. When we would come across a hard problem, it wasn't like, oh, shoot, I looked in the back of the book and there wasn't the answer, so I'll go to office hours, right? It was like, I looked in the back of the book and there wasn't the answer, and then I looked up 28 papers and read them, and now I have an idea of the topic, but I still don't have the answer. And then I go to talk to Bill, and he doesn't have the answer, and so we go find the answer from any number of other like collaborators. So I've got these faculty on here, six different people who I was always asking questions of, right? Because she was from, image processing, and he was from signal processing, and he was from optics, and so on and so forth, right? You just need, as your problem gets harder and harder, you need more and more topics involved. The fact that we have 2 engineering programs here at Grove City is a little bit arbitrary, right? We could have 20 if we decided to cut us all up into our topics, or we could have 1 if we just called it, you want to be an engineer? We'll train you in the engineering problem-solving skills that you need, because there's not a whole lot of problems out there that are so simple that one discipline can take care of them by themselves. Certainly, there's no problems out there that are so simple that you can take care of it by yourself. And so graduate school was definitely a broadening experience for me in the sense that I've kind of realized that, probably for the first time. Okay, so I'm very hardware-oriented, so I really enjoyed the lab aspect of grad school. You've got options. You can go to grad school and sit at a computer and crunch simulations all day, and somebody will be really happy you do that. Or you can go and you can do much more hardware-oriented stuff. Grad school research labs are oftentimes where the first prototype is going out into the field. So this has never been done before. I need to be a good enough mechanical engineer and a good enough electronics engineer and a good enough robotics engineer that I can make prototype 0 and get it out there. So, okay, I think that's more about broadening. I will say graduate school is like the first time where I ever really realized that I needed to be a scientist, or I'll say it made me a scientist, because it reshaped the way I thought about engineering. I think before I thought like engineering is getting a problem and seeing who solved it before and then asking them or looking in the back of the book so that then I knew the solution. And I think graduate school changed the way I thought of it, where now I think of it more like, well, engineering is somehow fitting the lock of the physics of the world around us with the key of all the different technologies that we have. So it's like this constant learning process, right? You come up to a problem, and the problem's got a lock on it, of probably a physics-oriented lock. And then you've got some toolbox of technologies that you know, so you see if any of those keys fit. And if none of them do, it's time to learn a new technology. It's time to learn a new key, right? So constant learning, I guess, is maybe the theme there, as echoing Dr. Richards and Brooks. So this is a brief plug that if any of you guys are interested in working in optics, 3D sensing, LiDAR, autonomy, I would love to talk with you about working on projects with you. I think project engineering, project-oriented engineering in the undergraduates all the way down to sophomore year and up, I'd say, is a big way to, number one, inform yourself about what kind of engineering you want to do, especially if you want to do R&D, and number two, just a way to keep yourself interested and your spirit of engineering alive as you sit in classes for many hours a day and you do your work and you do your homework, and that's all correct and good, but it really it can round out the experience for you. So if any of you are interested in doing projects around any of those topics that I mentioned, I'd love to talk with you about it, and I do not care what degree you're going to get at the end of the 4 years. Okay. All right, so now I do this, and I wanted to briefly mention, first of all, that the penguins are awesome, and second of all, that if you're a student who's considering graduate school, if you're the one, you know, you guys are the ones sitting in the seats there, so if you're considering graduate school, I would really highly recommend like doing some kind of faculty research, some kind of extracurricular, you know, you can do it as an independent study, independent research, but extra classroom experience, because I think that's really going to inform your direction. You know, you'll find out whether you like it, essentially. You'll find out whether you like being in that relatively open-ended, kind of scary open-ended situation, or whether you'd really, you know, that's not for you, and either one's fine. But the other thing is that graduate schools are competitive, at least to some extent. Again, you're looking for money to go to graduate school, so anytime you're asking for money for someone, they want to know what sets you apart from people around you, right? So, so undergraduate research experiences, especially if you find opportunity to publish, are sort of the currency of the realm, where you'll be able to say, well, hello, Penn State, I'd like to come and do, you know, material science PhD or whatever it is, and you should believe that I'm a credible R&D engineer because I've got 2 papers with Dr. So-and-so, and I went to a conference last year, and so I'll fit right into your lab, and here's the skills I'm bringing, right? So if you can say that with some self-trust, then that'll allow you to find lots of open doors and walk through them, hopefully. So I would really recommend that. The other thing about R&D or extra classroom experiences is that it helps direct you, right? You'll at least find out whether you like something. If you take my signals class and you hate it, you might just hate me. You know, you may or may not hate signal analysis or signal processing. You know, you're dealing with, or you might hate my textbook. You know what I mean? Like taking a class in something is a pretty narrow way to experience a field. So if there's something that really you think appeals to you, doing projects in it can help confirm or deny that suspicion, right? Then the third thing is looking for scholarships and fellowships. If you're really serious about grad school and you'd like to be on and it's because you'd like to be on the cutting edge of technology, then it behooves you to look around for those Goldwater fellowships, Fulbright scholarships, those sorts of things, and maybe we should talk about that. So, okay, I wanted to end, almost done. I wanted to end by briefly hopping over to a talk that I gave to some high schoolers a couple weeks ago, and I was talking to them about what being an engineer is, and so I was flipping through like creative problem solving, right? And I sort of tried to define engineering as creative problem solving. And so I was talking about, yeah, there's biomedical engineering, electrical engineering, blah, 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 mechanical, optical. And I was like being pretty arbitrary, right? Like, is this a mechanical engineering problem? I don't know. It's aerospace, it's electrical, it's materials, right? The world's pretty cross-disciplinary. Yeah, civil engineering. Tell a civil engineer to build a building by himself with no electrical engineers and see what happens. So obviously the world's a very cross-disciplinary place. But what I wanted to say was, when I got to here, you know, I was talking to them about what kind of person might really enjoy engineering in general, right? And it's the kind of person probably who is happy when they're being patiently, when they're exhibiting some patient focus and they're like concentrating on one thing for a while. They're curious, they're careful, and they have, you know, some team spirit to them. And basically, I just want to say, like, that all goes double for grad school. But what really probably goes the most double is patient focus and curiosity. Like, if you really just can't help but need to know, grad school is probably in your future. And then for skills, I told them, you know, you need physics, programming, blah, 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 hands-on. I think all of these can be really, can make you really successful in graduate school as well. It's really hard, like if you're just not willing to consider the math and physics of a situation, grad school is probably not going to work out. It's just, maybe somebody will hire you to program their stuff while somebody else figures out what the stuff should do. But for the most part, that physics and math interest is pretty necessary. And then understanding of nature, I suppose, with it. But all the rest, you know, really factor into success at the graduate level as well. So yeah, anyway, so I was happy I went. It was a lot of time alone in labs, but it was also a lot of time like meeting the best and the brightest and interacting with the best and the brightest and pushing as hard as I could on hard and challenging problems. And I found that very satisfying. So I think we're going to end there and adjourn for Q&A. Is that right? Yes. Yeah, okay. Well, thank you guys for your attention. Appreciate it.